we also come across other statements. For example, P only if Q. What is this statement says? P only if Q. So P is true and Q is false is false. That's what this says. P only if Q. You get to see that in a context P is true, whereas Q is false. And if that's the case, then the statement is false. And so P is true and Q is false, and is false then the truth value associated with the context is false. So happening of P must ensure Q follows. Happening of P should ensure Q is concluded. So P only if Q. So that's what this says. P is true and Q is false is false. And all other cases it is true. Okay. So we also look at this. Q follows, right? So Q follows from P, which means Q if P. Correct? Which means Q if not negation P. Correct? If not negation P, not of not. What is if not? If not is unless. Q unless negation P. So in natural language, you look at textbooks. Some textbook in a running context, they may say if A is an algorithm, then its time complexity can be measured using so and so. And if primality check can be computed in polynomial time, then so and so can be done. If you can solve traveling salesman problem in polynomial time, then it means something. They may say statement of this type. The same statement in a different textbook, they may say like P only if Q. So primality check only if some statement for Q. So all of them, all this 10 mean P implies Q. Either I can say P implies Q or I can use any of them. So for all of them, meaning remains the same. So these are all related. I am deriving one from the other. So Q follows from P, which means Q if P. If P is true, then Q must follow. That's what if P then Q. Now Q if P, and one can add negation. I'm saying if not negation P. And what is if not? It's precisely unless. So what is this telling me? Q follows, and unless negation P is true. Fine. So unless negation P is true. And if you go back, that's precisely this. If you go one level up, that's precisely this, which means all are one and the same. Correct? So just go through this and each of them very carefully. Also look at the lecture notes where you find some more examples. It's called Scribe. It is available in the website. Okay. And go through each of them in detail and some more examples. The details of each of them you will find in the Scribe. So we will see some more examples on biconditional operator, and then we will get into some logical argument involving these operators and other operators. Then we will look at the logical value associated with the argument. The closely related operator to implication operator is biconditional operator. This operator is an implication operator, also known as conditional operator. So when I say P, Q, and we combine them using this. This means this operator used to denote expressions of this type. P biconditional Q means P if and only if Q. The equivalent statements that we come across in computer science textbooks or in natural language, if P then Q and if Q then P. If P then Q is P implies Q, and if Q then P is Q implies P. And something that you see in mathematics textbook is the following. P is necessary and sufficient for Q. Okay. So we also say that something like this. P if Q and P only if Q. So P only if Q is P implies Q. P if Q is Q implies P. That's what this and this are saying. So this operator, we may either use this or all of this, and they all mean one. It's biconditional, and the way we have written this itself says you can find the truth value of this by finding truth value of this and truth value of this, combine them using the logical operator. That's what this statement says. So if this is true, this is true, true, false, false, true. So this says when both are true, it is true. When both are false, also it is true. When you have the other case, it is false. We can also derive this by taking the truth value of P imply Q and Q imply P and taking the logical AND between them. And the other way of seeing it is biconditional, and when both are true or when both are false, it is true, otherwise it is false. We will also derive by looking at the truth table of this, truth table of this, and combine them using this operator. Okay. For example, if you look at P implies Q and it is true, so this one is true, true, false is false, and when premise is false, irrespective of Q, statement is this. Then we look at Q implies P. True, true, it is true. Premise is false, you don't need to look at this, so it is always true. Premise is true, conclusion is this, so this is false. And premise is false, so it is true. Now you need to take a logical AND between them. When both are true, it is true. Even at least one is false, it is false. Both are true, it is true. That's precisely what we did before. So in a context, you find either simple conditional operator or implication operator, or you may find something like this and this that's equivalent to writing using biconditional operator. P if and only if Q, P is necessary and sufficient for Q, and so on. So we come across many mathematical statements, and to talk about the logical value associated with that, operator like this would be of very use. Okay, and having given the operators logical AND, OR, negation, exclusive OR, and conditional operator and biconditional operator, we shall now look at arguments involving these operators, how to find logical value to the given argument with the help of these truth tables. As always, we will convert the argument into symbols with the help of proportional variables. We will combine them using operators. Then we may get a big expression, and all that we need to do is construct a truth table of this type and start looking at the truth value of the given argument with the help of this truth table and the operator, which we shall see in detail now.